figure out how many pigs in pen A, pen B, pen C? When you know, raise your hand if you're willing to share. Can go home and tell people you counted pigs and pens today. Unexpected thing. All right, what do you have? A equals 9, B equals 5, C equals 3. Sound good? Okay, so how did you guys get these answers? What were you doing to figure it out? Be honest. Just share with me. Yeah. Just chose random numbers and worked it through. How many of you guys did that? Let's be totally honest. Yes, that's what I would do too, okay? That works really well for this problem because this is about pigs living in pens, so the numbers are positive, they're whole. If they weren't whole, it would be kind of a gross problem, okay? So it kind of narrows down the possibilities, like how many different numbers are there that can add up to 8? Not that many, so you can narrow down a possibility from there and figure out the rest, right? But what's going to happen? What if we change this problem to being about money and how much was in each account? And then all of a sudden we put stuff there. Would the problem be as easy to solve with guess and check? No, because what's going to be your issues if we're now saying, savings account A, savings account B, savings account C, and putting an amount between them? Yes. Yeah, decimals, right? Like, what am I supposed to guess? Like, this could be 1.25, this could be 1.35, this could be 1.37, it could be, right? Yes, sir. What's that? Negative numbers, okay? What if you spend a lot of money, right? You could be in debt in one of those accounts, and then we'd have to account for that. Can you imagine trying to then guess and check the possibilities there? Okay? It wouldn't be so fun, right? So what we want to try and do is establish an algebraic way when we have lots of things that are unknown to figure it out when guess and check is not going to be the most effective way. Okay? So let's talk a little bit about that. If we were going to solve this problem algebraically, all right. If we were going to solve the problem algebraically, we had pig pen A, pig pen B, and pig pen C. And when we look back at that last puzzle, we can tell that 14 means what? A plus B has to equal 14. So there's an algebraic equation that gives us a piece of information. A plus B has to equal 14. Okay? What else can you tell me about this puzzle? Yep. Good. 12 is equal to A plus C, right? I'm going to go ahead and write that down too. I like to keep my variables in order. Okay. I like to be super organized, all right? What else can we determine here? Yes? B plus C equals 8. Okay, so B plus C equals 8. So we've solved systems of equations in Algebra 1, and that's basically what we've created here. More than one equation that all pertain to a problem, okay? And we actually need these equations because can I do what I did in Algebra 1? Can I just use substitution or elimination with those two equations and have the answer for A and B and C? No. If it was just A's and B's, would that work? Absolutely. But bringing in a new variable means I need more equations to help me solve it, right? The more unknowns there are, the more patterns or connections I need to be able to actually solve the equation. So given that we have 3 unknowns here, we've been able to build 3 equations, and we're going to see if that can help us because we know just relying on 2 isn't going to do it, okay? So what could we do? Does anyone have any ideas about using the same process from Algebra 1, substitution or elimination, but making it work for this system that's a little bit more complicated? Can you combine these 2 together at all? Does it get you anywhere? What happens if you do combine these 2 together? Okay, so if we just combine them together as they are, we would get 2A plus B plus C equals a number. That seems super complicated, right? But can we do something with them so that when we combine them together, rather than getting more complicated, it gets a little bit simpler when we combine them together? Yes, sir? find one of the variables and substitute it in each equation. So let's say in this first one, I decide that A is equal to 14 minus B. Is that okay with everybody? I just rewrote it in terms of A, kind of like what you did on your summer packet, solve an equation for a certain variable. Now, what if I take that and I plug it back in for A right here? Then this equation is going to become no longer A, in place of A, 14 minus B, plus C equals 12. Now let me clean that up a little bit, right? I'll move all the constants together. If I do that, I would have a negative B plus a C equals, if I subtract 14 from both sides, negative 2. Okay? So I still use the suggested idea. I combined them together, but I kind of was manipulative about the way I wanted to do it, right? I made some deliberate choices. How does getting this equation help me? It still did not solve the problem completely, but this is a big step in the right direction. How does this new equation help me? Sure. Now, this equation can be combined with this one that wasn't used to make it, so it should be just fine. And when I combine those two together, so I have B plus C equals 8, and I have negative B plus C equals negative 2, I get 2C equals 6, so C is equal to 3. Okay? Now that I know that C is equal to 3, what am I going to do with that information? Plug it in, right? Am I going to go here first to plug it in? No. Go to a place that uses it and only one other thing so you can figure out the one other thing, right? So maybe I come here. B plus C equals 8. If C is 3, B plus 3 equals 8, then B must be 5. Now that I know B is 5, what's the only thing I haven't figured out yet? A, I'm going to take one of these two pieces of information. I can either use that C is 3 here to solve for A, or that B is 5 here to solve for A, but either way, I would plug that in and I would be able to get that A is equal to 9. Okay? Again, is this the fastest way to do the pig pen problem? No. But do I have a point in showing you how algebra can be used in these problems? Yeah, because real life isn't like pigs all the time, okay? It gets super messy, decimals, negatives, all these crazy numbers, where all of a sudden guess and check becomes like an impossible task, okay? So then we have something algebraic to fall back on, okay? But of course, it gets a little more complicated. This was just our introductory, okay? So you can put your math moments away. I don't care if you take today's notes on the math moment, but know that I collect them and they don't always get back as fast. I tend to not collect your note guides because you guys like to keep them for reference throughout the year. So the next thing we're going to do is we're going to take your notes on a couple more complicated problems. We're going to skip right to example 2. I talked to Miss Brady. I know how far her class got, so I'm not going to start with example 1. I'm going to start with example 2 because we can do it, and it's going to help us with a harder idea, okay? All right. So here's 3 equations with 3 unknowns. They are ugly, right? Okay? Big key in this. Most students, because you guys have done Algebra 1, you've done elimination, substitution with smaller systems, get the idea. The reason they miss these problems is usually strictly an organizational thing, okay? Or an arithmetic error. Like they don't add right, they don't multiply right, okay? Or they get lost because there's a lot of steps, all right? Usually the big idea everyone gets. All right, so first thing that bugs me up here is the third equation, okay? I'm not a big fan of fractions. What can I do to rewrite that equation in a way that I don't have to deal with the fractions? Yes? Good. Multiply the equation by 3. Luckily, they all have a denominator of 3, so that wasn't such a hard decision. So I'm going to multiply the entire equation by 3. Don't like that I can't reach it. Whatever. I'll do it right there. So when I multiply this third equation by 3, remember that means both sides, all terms on each side. Okay. So 2/3 times 3 is just going to leave us with 2x. 3 times negative y will be negative 3y. 3 times z over 3 will just be plus z, and 3 times negative 1/3 will be negative 1. This is the same thing as what is written up there, okay? So I'm basically going to say this is my third equation that I am now going to try to use with the other two equations that were written there. And those original two equations I'm just going to write here so that I can see them and write them better. This was equation number 1. The little numbers I'm putting next to them are just the order they were given in the problem, so that if you guys tell me, oh, do this, I can know which equation you're talking about. This was equation number 2. So here's my 3 equations with the third one rewritten without a fraction. Okay? So we could see how guess and check could be hard here. You could guess an x, y, z that could work in the first equation, but will it work in the second one and the third one? It would go all over the place. Okay? So instead, we want to use substitution or elimination to help us through this process. Okay? So for example, one thing that we could do, I'll help you guys through this one, you guys help me through the second one, and then we'll let you guys start working individually and talking with your groups, okay? I'm going to choose a variable to eliminate. I'm kind of a big fan of elimination when I don't have to use substitution. Sorry. Okay? Because in these, you got to move multiple, and then you got to like divide by numbers, and then you get fractions back again that you didn't want in the problem, okay? So I try to use elimination where I can. Sometimes it's the best, sometimes it's not the best. With the pig pens, I think substitution was the way to go because the numbers were simple, okay? So I'm going to make a decision if I want to try and focus on eliminating x, y, or z, okay? Does anybody want to help me with this decision? Do you see a place? Okay? And then combine it with which one? The last one? Okay, in order to eliminate x and z. Well, the first and the last, yeah, that will actually work. Okay, so you mean the third, yeah, the first and the last, right? Yeah, okay. So multiply one of these by a negative. So that's going to give us negative 2x plus 3y minus z equals 1. I'm not going to multiply this other one by anything. She was aiming to get rid of x's, and in this case, x's and z's possibly at the same time. Okay. So the second equation says 2x plus y plus z equals 7. The first equation. Shouldn't have written them in this order. All right, so she's right. Our x's and our z's eliminate, leaving us with 4y equals 8. And therefore, y is equal to 2. This is not my final solution. I just like to put a circle around it so that after I'm done with all this crazy work, I can find my values of x, y, and z rather quickly. Okay, so it's just an organizational thing. It's not like a declaration of like, this is the solution, okay, because we're not done. All right, so we have found a y value of 2. What would we like to do with that? Somebody new. What do we want to do? What can you do if you know that y is 2? Yep. Sure. So we can substitute the y. Now, when we substitute the y in the second equation here, it's not as nice as the pig pens, right? We substitute it in, and we get something simpler, but do we find x or z automatically? No. So we're still going to probably have to use systems. Well, let's go ahead and do what she said. Let's substitute that 2 value for y right there. Okay. So that equation is now going to say 2x plus 2 plus z equals 7. And if I move the 2 to the other side with the 7, I have 2x plus z equals 5. Okay? Organizationally, it kind of sucks to have all this stuff. Sometimes it's hard to keep track. You might want to like cross that off or something like that. Sure. So we can move 2x to the other side to get z. So we could say that this is z is equal to negative 2x plus 5. Oops. Okay. And if we have that, okay, then we can plug that back into any other equation. Now, we don't want to plug it into this one because that's the one that we rearranged that from. So if you plug it back in there, things are just going to like cancel all out and stuff like this. You're not going to get anywhere. But we can plug it back into another equation. Would you guys like to plug it into the equation that's numbered number 2 or the one that's numbered number 3? 3? I'm with you there. Because z doesn't have a coefficient, then I don't have to distribute, right? Okay. I'm good with that choice. All right, I can also at the same time, I know that y is 2, right? So I'm going to substitute for z this equation. And I'm not going to forget that I already know that y is 2, so I'm going to be able to substitute both of these things with either a numerical value or something that's about x. So in the end, this equation will only have x's as the variables, which will give me where I want to be, okay, another place to solve. So if I go ahead and plug that in, I'm going to have 2x minus 3y, but y is 2, plus z, but z is equal to negative 2x plus 5. And that is supposed to equal negative 1. All right, so I'll work on this a little bit. 2x minus 6 minus 2x plus 5 equals negative 1. But what happens here? Yes? The x's cancel, and all I get is that negative 1 is equal to negative 1, which is true, but it didn't help me find x. So why do we think that didn't work? Why do we think that maybe didn't help me find x? Yes, sir?
Does x equal all real numbers?
In some cases, yes, but not necessarily in this case. Usually if you're going to get a bunch of, it wouldn't be everything. It would just say like infinitely many solutions. And that would usually happen. You wouldn't have a specific y value. So because we have a specific y value, I know I'm headed towards one, like, not ordered pair, but like ordered triplet, like an x, a y, and a z. Okay? But I don't know which one. So the reason this isn't working the way we want has to do with the fact that we're using 1 and 3. And we were using 1 and 3 at the beginning. So we're just kind of going around in a circle with our information. Okay? Another option for us, okay, so we got to the place where z is equal to negative 2x plus 5. We can try plugging it in here. If we plug it in here, are the x's going to cancel out? No. Okay, so I was with you. I wanted to do the easier equation, but it didn't give us the work we need. So we need to go back and try something else. And again, why that didn't work is because we used these two equations to make this equation and solve for this, and then we're trying to use it again. And so it's giving us some trouble there. So what if we try it here? So 12x minus 2y minus 2z. Okay. So now let's see what happens. We have 12x minus 4. If you see me make an arithmetic mistake, stop me. So like you should do it on your paper too. Minus 10 equals 2. So we have 16x minus 14 equals 2. So 16x equals 16. So x is equal to 1. Am I good? Can someone confirm they did the substitution and they got 1 also? Good? Okay. All right. Again, I'm going to circle it so I don't lose track. So now I know that x and y are 1. Or excuse me, x is 1, y is 2. I can plug lots of things in here. I can go back to any of these and plug in x and y. I can go to this equation where we solved for z and just plug x in right here, okay, to find z. I have lots of options for where I want to plug in. What do you guys want to do? Over there? Just plug in the simple one? Okay. So what if I try to take this equation, okay, and to find z, I plug in this value of x. Then I would get that z is equal to 3. Okay, so my answer to this problem is going to look like an ordered pair, but it's an ordered triplet. X is 1, y is 2, z is 3. Who would know the answer is just 1, 2, 3? Okay, if I want to check and see if my answer is correct, what do I need to do? Yes? Okay, but not just one of the equations. How many of them? All 3 of them. If this is a solution to this system, it doesn't just work in one of those equations. It works in all 3 of the equations. Okay? All right, I'm just going to say one other thing about this example. I want you guys to get to start in class. So what would be more difficult for you guys about this problem? Yes. Good. Not all of the variables are in each equation. So let's just talk about approaches. Okay? What is something you could do that would work? So like what is something I could do if I decided that at the beginning of the equation I was going to combine together the first and second equation to get something that later I can use with the third equation. What would I really be trying to do with the first and second equation? What's the only thing I can do with those? Big idea, not like multiply by this or something like that. Just what would I be trying to eliminate if I want to use my answer after the first two are combined to work with the third equation that's up there? The S. Because if I want it to be something useful to use later with the third equation only has R and T, right? If I want to use substitution or elimination, I want to either substitute something for R that just has T's, something for T that just has R's, or I want to be able to cancel out R or T. So is it going to help me if I combine the first two together and keep the S? No, that's just going to add a new thing to the third one, okay? What if I didn't do that approach, okay? What if I decided I wanted to combine together the first and the third equation, okay? What would I probably want to do with those to produce something that's usable later on with the second equation? So if my first step is to take the first equation and the third equation, but long term I want to use it with the second one later, what am I thinking? Yes, sir. I would get rid of the R, okay? Because if I want to use it with the second equation later, what does the second equation have in it? S and T. So I want another equation with S and T to be able to do substitution or elimination with that. Does that make sense? So when there's less variables, it's actually less work, but sometimes it kind of boggles our mind because everything doesn't just like line up all nicely where we can like start eliminating stuff, okay? So there's no set rule for how to do this. You guys can do substitution or elimination, but it's basically doubly long process, right? We usually start with like 3 equations, and then we're maybe combining these two together to get some new equation, but does that usually solve for X or Y or Z right away? Not necessarily. Then maybe I put together some other two, either these two or those two, okay? And I make a second equation. Again, does that one probably solve right away for me for X or Y or Z or R or S or T? No. But then usually my goal is to, once I've made these two smaller equations, if they have matching variables, it is now an Algebra 1 problem, right? I can use substitution or elimination with just X and Y, or just Y and Z, or just R and T. That is my goal. Does that make sense? So same processes as before, more complicated problem, but really just stay organized and be prepared to do more steps throughout the problem. Okay? So I'm going to give a class set of the handout, which means you'll each get your own. Okay? But I want it back